Uh, Hello and welcome to this lecture series on signals and systems. So we'll be starting with the frequency analysis. Fine. So like I mentioned in the previous video, the representation and the analysis of LTI systems as we did in the second chapter, it was based on convolution sum and convolution integral. For the discrete time case, it was convolution sum. For the continuous time case, it was this convolution integral. But the starting point was that we represented signals as linear combination of impulses, as shifted impulses to be precise. Right? Now, since impulse was purely defined in time domain, so your analysis was purely from the time domain point of view. Now, an alternate representation of signals in LTI systems, it can be by expressing the signal x of t in terms of linear combinations of complex exponentials. Right? We can do it. And this would introduce the frequency parameter. And the resulting analysis, the resulting representation, if we represent x of t as a linear combination of complex exponentials, it is basically Fourier series and the Fourier. So let me just put some lines here. So we will be doing, this will be the frequency analysis. And as a starting point, we will be expressing our input signal it will be expressed as a linear combination of complex exponential signals. We have already studied this signal in our first chapter. Fine. And the representation, it will be typically Fourier series. Yeah, Fourier transform. We will discuss what is the difference between the two. Fine. And there are actually four distinct Fourier representations. Fine. Fine. And each one is applicable to a different class of signals. Right? Now, we did one classification of signals and we classified signals as, this was one of the basic classifications that we did, that we can have a periodic signal or we may have a signal which is not periodic. Fine, we can say aperiodic and non-periodic. Fine. Okay. And again, then a periodic signal, it may be continuous in time or discrete in time. So if we go for further classification, you may have periodic, which is continuous in time, discrete in time. Same classification for aperiodic, it may be continuous in time or it may be discrete in time. Right? Now, what kind of Fourier analysis you will be using, it depends on these two properties, periodicity and the continuity and discreteness in time. Right? Now, if your signal is periodic and it is continuous in time, we will have the simple Fourier series analysis. You must have done it in your mathematical courses in your first and second semester. Fine. And if your signal is periodic but it is discrete time, so we will have a discrete time version of our Fourier series. So it will be discrete time Fourier series. So Fourier series expansions or Fourier series representations, they are reserved for the periodic signals. Fine, whether it's continuous time or discrete time. Now, if your signal is aperiodic, it doesn't have some fundamental period, it doesn't repeat itself. We have discussed the periodicity property in our first chapter. Then instead of Fourier series, we will be doing the frequency transformation. Yeah, you can call analysis or representation through the Fourier transform. So if it is the continuous time case, we will have the normal Fourier transform. Again, you might have done it in your mathematical courses. And in case it is a discrete time aperiodic signal, then we will have the discrete time version of the Fourier transform. So that's known as discrete time Fourier transform. Again, you will see a lot of symmetry. We'll be discussing this one in detail, the Fourier series, and we'll again discussing this, and you will see there's a lot of symmetry between these two. Like we have done in the second chapter, we did LTI analysis of the continuous time domain through the convolution integral. Then we took the discrete time, and there was a lot of symmetry. आपके जो generalizations थे, the way we express causality and stability in the continuous time case, there was a similar representation and similar kind of analysis in the discrete time case. And we're expecting that similarity here also. Similarly, when we'll be discussing Fourier transform for the continuous time case, then again there will be similarity between these two analysis. Now, फिलहाल के लिए this will be the part of your second chapter. Fine. So we will be sorry, it's not a second, third chapter. We'll be starting frequency analysis with the Fourier analysis, जिसमें ये चार cases बन जाते हैं. Fourier series for continuous time, discrete time, periodic signals. Fourier transform for continuous time, discrete time under the aperiodic signals. We'll be doing the properties and the analysis. Then we have, under frequency analysis, we have the Laplace transform. We will study that when we should apply Fourier transform. Yeah, why do we shift from Fourier transform to Laplace transform? So Laplace transform is dedicated explicitly to continuous time case, right? And that will be basically your fourth chapter. Again, it will be frequency analysis. Everything will be expressed in terms of exponentials, and that means frequency parameter will be involved. Then the discrete time version of Laplace transform, we don't have a discrete time version of Laplace transform, but we have another transform which goes by the name Z transform. तो जो एनालिसिस हम लैप्लस ट्रांसफॉर्म के थ्रू करते हैं कंटिन्यूस टाइम डोमेन में, सिमिलर काइंड ऑफ एनालिसिस इज डन फॉर द डिस्क्रीट टाइम डोमेन थ्रू दिस ट्रांसफॉर्म, and that will be your fifth chapter. So like I said in the previous video, your following chapters, third, fourth, and fifth, they will be purely based on frequency analysis. Difference is, third chapter में we'll be doing frequency analysis through Fourier. Fourth में we'll be doing frequency analysis through Laplace. That will be dedicated, and that will be explicitly reserved to continuous time case. And in the last one, we'll be doing frequency analysis through this Z transform that is reserved to discrete time domain. So फिलहाल के लिए we'll be starting with the Fourier series analysis. Yeah, we'll be first starting with the representation, and this will be for continuous time, and definitely it is going to be periodic signal. So we'll do the bit of analysis. We'll see how our systems, yeah, signals are rather represented using Fourier, and then things will follow how we actually analyze and what are the properties that we take once we are done with the representation. Now the starting point here is that your signal, first it should be periodic, right? And obviously it is continuous time. So if I define a continuous time signal x of t that is periodic, then it should follow this property. This is the basic condition for periodicity, right? And where t is the time period, after time t it will repeat itself. And with respect to this, we had defined two quantities. Again, if you go back to your first chapter, we had defined the fundamental period, and corresponding to fundamental period we had the fundamental frequency. So I will again define it here. The fundamental period for this signal, in this case of it will be for x of t, it is the minimum positive value of t for which, let's call it equation 1, for which this equation is satisfied. Fine. जो smallest value है t का, obviously there may be some higher values of t for which the signal is repeating, but जो smallest value, the smallest positive value of the t for which it repeats, the signal repeats itself, we call the fundamental period. And related to this fundamental period, we have the fundamental frequency. We'll be defining it as omega naught, and this is simply 2 pi by t. Right? So we have the concept of fundamental period as the minimum positive value of the time period t for which the signal repeats, and then it is related to this frequency through this relationship. Right? Now we have some basic periodic signals that we have discussed in our first chapter, like we have the simple sinusoidal signal cos omega naught t. So this will be a periodic signal with fundamental frequency omega naught. Similarly, we had defined a signal, the exponential signal, x of t e raised power j omega naught t. This is a complex exponential signal. Fine. Now both these signals, this one and this one, let's call it 2, they are periodic, obviously, because it's a continuous time domain. Discrete time domain where we have to look for a particular condition, but right now this is the continuous time domain. So both these signals are periodic and they have a fundamental frequency omega naught, which is equivalent to 2 pi by t. Right? Now if I define a series of signal, we have x of t is equal to e raised power j omega naught t. I will define a series, a signal. I will represent it by phi subscript k as a function of time, e raised power j k omega naught t, right? Where k is equivalent to 0, plus minus 1, plus minus 2, dot dot dot. So it will be positive negative values of these integers. So let's call it 3. I am defining a signal phi subscript kt. It's also an exponential signal, just that I have added a parameter k which can take these values. Right? Now if I check periodicity on this particular signal, mean I have this signal, let me check what is phi k t plus t. So it will be e raised power j k omega naught t plus t. Then I will do a bit of rearranging of terms, j k omega naught t into e raised power j k omega naught capital T. Right? And this will be equivalent to e raised power j k omega naught t into e raised power j k omega naught. अब इस t के बदले I can use this 2 pi by omega naught. So for t, I'll be using 2 pi by omega naught because t is the fundamental period. So this and this will go. I will have e raised power j k omega naught t into e raised power j k 2 pi. Okay. Now this part, e raised power j k 2 pi. If I give different values of this, because k can take these values. So from this I can have e raised power 0, I can have e raised power j2 pi for plus 1, e raised power minus j2 pi for minus 1. Similarly, e raised power j4 pi, e raised power minus j4 pi, and likewise. And all these signals, they are equivalent to 1. Fine. This is a complex exponential. So for these values, for even values of pi, it is equivalent to 1. Fine. So this means this part is equivalent to 1 for k is equivalent to 0 plus minus 1 plus minus 2 dot 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 जो भी values आप देंगे. So it turns out that my phi k t plus capital T is equivalent to e raised power j k omega naught t. और आपका जो मैंने डिफाइन किया था phi kt, it is also equivalent to j k omega naught t. Here j k omega naught t, this is also equivalent to this. ठीक है. So it means that this signal that I defined, phi of kt, which will have different values depending upon the value of k, is also periodic with period t, capital T, right? Right? We just proved it using this small analysis. But what about the fundamental frequency? This simple complex exponential x of t e raised power j omega naught t, it was also periodic with period t, and it had a fundamental frequency of omega naught. Now we have done a bit of mathematical analysis. It turns out that phi kt is also periodic with period t, but we need to find what the fundamental frequency is. So just as an example, if I take this signal phi 3t, जहाँ पे k का वैल्यू 3 है, so it will be j3 omega naught t, fine. And we'll do one thing, we will do phi of 3 t plus t by 3. Okay, so it will be e raised power 3 j omega naught t plus t by 3. So again, if you do a bit of rearranging of terms, 3 j omega naught t into e raised power j omega naught t, it will be e3 j omega naught t, because this factor will be equivalent to 1. So it turns out it is periodic with t by 3. So generally what happens that when I define a new class of signals which are related to this kind, like this, it will have a period t, जो इसका fundamental period होगा, fundamental period of phi kt is fraction of t. In fact, it is t by k, like in this case t by 3, fine. So if I have a normal exponential x of t is equivalent to e raised power j omega naught t, इसका जो fundamental period है, it is t, which is related to omega naught like this. And if I define a new series of exponentials phi kt as e raised power j k omega naught t, it will have a fundamental period t by k, which will be 2 pi by omega naught k. Having said this, it will also be periodic with period t. Please remember, we define fundamental period as the smallest value of this time period, smallest positive value for which the signal repeats. So although this signal is again periodic with period t, but इसका जो fundamental period है, it is a fraction of this period t. Okay? So we kind of establish a relationship between the signal x of t, which is pure exponential, and a new signal which is again exponential, but it has a parameter k. Okay? So we can say here, क्योंकि alternately speaking, omega naught will be simply 2 pi by t, and यहाँ पे omega naught will be 2 pi by, if you do this kind of 2 pi, it is omega and this. So you can do a similar analysis. इसका time period ये है, then so there will be a parameter t will be involved. So what I'm trying to say here is that each of these signals, so each of the signals phi of k it will have a fundamental frequency, fundamental period, one of the same thing, that is a multiple of omega naught, which is the fundamental frequency of your simple exponential, right? So we say they are harmonically related. Harmonic is the term which we use in terms of frequency. Okay, so this signal x of t and phi of k of t, which we have just come up with, they are harmonically related, and the relation is this: इसमें भी t involved है, इसमें भी t involved है. This has a fundamental period t. This also has a fundamental period which is a fraction of this t. Not only that, इसका fundamental period is also the period for this newly found signal. So they have these Zariski fundamental frequencies that they are kind of related by the parameter k. So we say that the signal x of t is harmonically related to the signal phi of k of t. Okay? And now if I express, so as a next step, I will express a signal, a linear combination of these harmonically related complex exponentials. Means I will come up with a signal x of t, which is actually a summation, a linear combination of these kind of signals. Fine. Now जो इसमें individual signals होंगी, it will have signals like e j omega naught t, then it will be e twice j omega naught t. We have just concluded that they are harmonically related. Now if you have a periodic signal, if you have 2 or 3 periodic signals, the sum of their periodic signals will also be periodic. So I'm expressing a signal x of t, which by the way is my input, as a linear combination of these harmonically related complex exponentials. Fine. So ये जो summation होगा, this will also be periodic. This is also periodic with period t. And this kind of representation is known as Fourier series representation. Right? I will end this video, and the next video will be further trying to understand what physically we mean by this kind of representation.